Okay, so I have an example here, a moderately complicated one, of applying several of the concepts that we studied in the previous recordings about Kirchoffs laws. And this is actually going to combine concepts from not only the Kirchoffs loop rule lectures, but also from the multiple resistors series of lectures. So I have already set it up. So I have this circuit you can see here. So I've got 4 resistors with 1 battery, and we have a combination of resistors that are in series and in parallel, and we have some that are actually neither. Here are the numeric values. R1 is 5.6 ohms. I didn't put the unit here. R2, R3, and R4 all happen to be equal in this example at 16.8 ohms. And so the question is rather specific: to calculate the current that passes through R2. Why that one? Who knows? One of these artificial textbook problems. I suppose in a real circuit, you would want to know whether this device would operate correctly if it was wired together like this. All right, to tackle this thing, we need some general concepts. The approach that we're going to take is to simplify down this moderately complicated collection of resistors. Getting my head out of the way so you can see the statement of the problem. Oh yeah, part B, calculate the total power output by the battery. So we'll have to look into that. The 3 resistors here are in some sort of complicated relationship and arrangement, and then of course with R1 here. And so the general strategy that we're going to take is to try to eliminate capacitors that are in resistors that are in parallel with each other by finding their equivalent resistance. Once that's done, then we will take resistors that are in series with each other, calculate their equivalent resistance, and we keep iterating that process until we get only one equivalent resistance for the entire circuit. Now, the question is, how do you decide whether 2 or more resistors are in series or are in parallel? And there are 2 rules that will guide you here. So the first one is 2 components, 2 electrical components. In this case, we only have resistors, but the statement that I'm about to write down holds true not just for resistors, but for capacitors, and then later on in your education, inductors, and pretty much anything else. Right. So 2 components are in series with each other. The current through each component must be the same. So I've underlined crucial ideas here. First of all, series. Second of all, the judgment as to whether we have components in series or not depends on the current. And the reason I mention that is because the next rule that I'm going to talk about will refer to the potential difference. So anyway, if the current that flows through each component must be the same, then we say that those electrical components, resistors in this case, must be in series with each other. On the other hand, 2 components are in parallel. If the same potential drop happens across each. So those are our touchstone rules. Those are how we evaluate whether objects are in series, whether they're in parallel. And it's entirely possible, by the way, for two components to be neither in series nor in parallel. So let's take a look. So let's consider a current. And the first step, I guess, is to choose a reference point in the circuit path to use to write down the sequence of changes of potential, add all together, apply Kirchoffs loop rules. Obviously, we've got some branches here, so we're going to have to do both the second loop rule as well as the first loop rule. So I'm going to choose an arbitrary point. Let's start here and go counterclockwise around the circuit. All right, so we will call this current I1. And when the current arrives at this branch point, it will split. And the labels are pretty arbitrary here. And I will have this current. This is a little bit complicated. So this current here that flows through resistor number 3, I will call that R3. And the current that flows through resistor number 2, I will call that current I2. And then finally, this current here, I will call this I4. And the currents will rejoin. Now, I'm playing a little bit fast and loose here because the current splits here, and then this current really here should split into two subcurrents, and I suppose I probably should color this a different color. I don't know how many other colors I have here. So I have orange. Maybe the orange will work. I don't know. So there's a current there. But notice that whatever current this little bit is right here, by Kirchoffs' second loop rule, the total current that goes into a branch, subcircuit, has to come back out of that branch. And so this is going to be the orange current also. And I could label that, I suppose, but the truth is it's this current and this current, the orange bits, neither of them are actually going through any electrical devices. And so there's not a lot of value in it. And this is not something that you would necessarily know right off the top of your head, but this is why you take class, to learn little tricks like this. So broadly speaking, if a particular subcurrent doesn't actually pass through an electrical component, probably you don't need to worry about it. And so I'll just suppose that this, well, in fact, frankly, I could move this branch point over to here, and then there wouldn't be any subcurrent, this little current here at all, and I could move this branch point down to here. Okay, so really these orange currents are nothing to worry about, nothing to think about. We don't need them. I'll put them there for completeness, just for the sake of the drawing, but really they don't come into play in any mathematical or really any physical sense either. Right, so the current splits here, and we get this current here. So we have 1, 2, 3, so 4 currents. But of course, this current here, what happens is, so the brown and orange rejoin here, that's our blue current once again. So that comes back out here, and this will be our total current I. Once again, flowing, we're going to assume, like this. And as I've said before, when we calculate currents, when we do the math, we may end up with a negative number for different circuit values, for different current values. If so, that simply means that the current flows in the opposite direction of what we chose when we set up our drawings. Okay, so that's the first step in solving this complicated problem, is simply identifying where the currents go and putting down labels. Okay. Now, as far as these two statements are these two guidelines, these two touchstones are concerned, let's take a look. So series with the same current flows through each of them. Well, a nice advantage to having colored it the way I did is that I can see at a glance that I don't have really, I don't have any series resistors, or at least not obviously I don't. Okay, so just look at the colors. None of the resistors are colored the same color. Therefore, none of them must have the same current flowing through each of them. That's what the coloring code means. And therefore, none of these are in series with each other. Now, that statement is a little bit strong, as you will see. I mean, it's true, but, well, let me just go through it, and I'll point out where I was being a little excessive here. Okay, so none of them are in series, at least on the surface. Okay, how about in parallel? Do we have anything that the same potential difference? The answer there is, oh yeah, definitely, because it goes like this. Suppose I took a voltage probe and I put, let's see, this is the positive side of the battery, so I put the red probe here and I put my black probe there. Stare at that for a moment, and you should be able to convince yourself that I'm going to get just one single reading for a potential drop, and that same potential drop will occur across R2, R3, and R4. Okay? So R2, R3, R4 have the same delta V, the same potential drop. Therefore, by this rule here, they are in fact in parallel. And that means in turn that I now know how to calculate the equivalent resistance of these three. So they're in parallel with each other, so we use that reciprocal relationship. So that's good. So let's do that. So the answer, so the next step is start simplifying down your complicated resistor network by identifying things that are in series or are in parallel and finding the equivalent resistances of those sub-networks of just parallel or just series. We didn't find any, sorry about that, we didn't find any series resistors, but we do find parallel, so let's find the equivalent resistance of these parallel components anyway, these parallel resistors. Okay, well, presumptively you remember how to do that. Okay, so first, we call this R sub EQ dash P or underscore P. R2, R3, R4. They're all in parallel with each other. And that's easy enough. It's simply R equivalent dash P. Let me do it in slow motion, I guess. The reciprocal relationship, remember? So it's the sum of the reciprocals. And I'm going to be lazy. And then I take the reciprocal both sides. And you'll see in a few minutes why I feel justified in being lazy. Obviously, I just took the reciprocal of this relationship there. Okay, so there's that. Now, this isn't anything like an answer. This is just an important step along the road to an answer. Okay, so we've got, so what this means is that, if I substitute in those numbers there, I'd get a numeric value for this resistance, and that means I could cut those three resistors, those three parallel resistors out of the circuit, replace them with one resistor of this numeric value here, this number of ohms, and the circuit would behave exactly the same way. Difference, of course, is that by the circuit would behave the same way, what I actually mean is only the battery would put out the same current. but obviously we actually care about operating whatever resistor R2 happens to be. So anyway, so equivalent resistance for the 3 parallel. And then the next step in simplifying down the resistor network is find the equivalent resistance of the whole sequence. Now, let's go back here. As I said just a moment ago, as far as the battery is concerned anyway, I could cut these 3 resistors out of the circuit, replace them with just a resistor with a number of ohms equal to R sub EQ dash P, and I'd get the same current out of the battery. That means, but if I did that, if I replaced all of this with just one single equivalent resistor, then that one resistor, this current would come in, this same total blue current, I, would go through that one equivalent resistor, go through resistor R1. In short, the same current would pass through the equivalent resistor as passes through R1, and thus, by the first rule, those 2 resistors would be in series with each other. It's this that I was thinking of earlier when I said that I was saying it a little strongly when I said that none of these resistors are in series. That's true for the initial diagram, but when I replace these 3 parallel resistors with one single equivalent resistor, that equivalent resistor would be in series with R1, and so then we can calculate the equivalent resistance by simply adding them, which I will now do. So the R equivalent for the whole circuit is simply R1 plus R equivalent underscore P, okay, which is that there. So that's then the entire equivalent resistance. As far as the battery is concerned, that's how much resistance there is in the entire circuit. Okay? And therefore, there's 2 ways of looking at the total current. First one is to say, using Ohm's law, I equals V over R equivalent. Okay, R equivalent is this, where this is that. So moderately complicated. Okay, and there's that, which is nice, but it isn't the question that I actually originally asked. It will turn out that I will need this number for part B, but we're still on part A. Part A is, what is the current that flows through just resistor number 2? Okay. So what we're going to have to do in order to answer that question is apply Kirchoffs' first loop rule to several of the subbranches. To get I2, well, I2 involves current I3, I4, and the total current I. All right, so we have basically 3 unknown currents: I2, I3, I4, I2, I3, I4, and so we need 3 equations with 3 unknowns. And we will get that by applying Kirchoffs' first loop rule to 3 of these loops, and I'm going to choose the outer loop, the inner loop through through R3, and then this other inner loop through R2. So in other words, I'm going to go through R4, through R3, through R2. Okay, I'm going to write down Kirchoffs' first loop rule for that. That will give me the 3 equations I need. I think I'll start here. So the first part was the conversation that we just had for the last 5 or 8 minutes was for getting the total current output, which is good, and we're going to need that. But to get the individual current, we need to take a different approach. Okay. So our first equation, we're going to start here and go counterclockwise around the various loops. So do that. Okay, so I'm going to just write the equations down, I guess, in numeric order. We're going to go current I, and then I'm going to do I2, then I3, then I4. So equation 1, we're going to gain some potential when we cross the battery, go from low to high, and we're going to do the loop through I2. So our current is going to go through. The current that actually passes through R2, I've labeled that I2. So that'll be a potential drop of minus I2 times R2. And then we'll come around here. We're going to go through the outer loop. So nothing else happens until we get to R1. And so we have minus I times R1. And we're back to where we started. And that's equal to 0. So there's our first equation. Our second equation, we'll go through R3. So V minus, okay, we're going to R3, so we're over here. So I3 times R3 minus I3 times R3. Again, a reminder, this I times R is a potential drop, and that calculation comes from doing Ohm's law, V equals IR. Back here, once again, I times R1 minus I times R1. And a reminder that I is going to be the sum of all of these subcurrents, I1, I2, I3. I1 plus I2 plus I3 is going to equal I. So we're back to where we started. That's equal to 0. And then our third equation is V, and then we're going to R4. So the current I4 times R4. So I4 times R4 minus I times R1 is equal to 0. And our 3 unknowns here are the currents. With the reminder that I is equal to I1 plus I2 plus I3. So if I were to make that replacement, you can see that the equations are going to get very complicated very quickly. And if you think for a moment that I'm going to do this, that I'm going to solve this system of equations by hand, you don't obviously know me very well. No, I turned this over to Sage, and I asked it to do the calculation for me. And what would have taken me 2 hours to get wrong, it did in 2 nanoseconds and got right. And put it here. And I'm going to only write down the expression for I2, because that's the only thing the question actually asked for. I will post, however, the complete solution so that you can see it and admire it. But in any case, I2 can be shown, ICVS, it can be shown, that I2 as an algebraic expression is, do the denominator here first. So I'm just going to copy what Sage produced. R1 times R2 times R3 plus the quantity, R1, R2, plus the quantity, R1 plus R2, close quantity, times R3, close quantity, times R4. That's all in the denominator, and the numerator is V times R3 times R4. If I got that right, R3, R4, 1, 2, 3, R1, 2, plus R1, R2, R3, R4, yeah. And do a sanity check on the units. We expect the units to be amperes, so we should have potential in the numerator and resistance to the first power in the denominator. In the denominator, as you can see, each one of these factors is r to the third power, but in the numerator we've got r to the second power, so sure enough, we have r to the first power in the denominator and volts in the numerator. And substituting the given values, and I get I2 was equal to 0.34 amperes. And the positive sign means that the current does in fact flow the direction that I thought it did, or that I guessed that it did. So, okay, so that's that. And then just real quick, part B was the power output. I believe that's what I asked. Easy. I squared R equivalent. Okay, it's easy, but you have to know what you're talking about. First of all, the power is the total current put out by the battery. Well, the total current put out by the battery is what we've been calling capital I, which is either I1 plus I2 plus I3, or it can be calculated like this, okay? And so there's that. And then the power output is, there's some power output from each resistor, conservation of energy. We simply add those three together, and that's why we have R equivalent there, okay? And so then you just simply substitute in the given values, and I did that, and I got 11.8 joules per second, 11.8 watts. This is the Joule heating law. Depending on the order in which you've been watching these recordings, you may or may not have seen the Joule heating law. If you have seen it, then yay. If you haven't seen it, this is the Joule heating law. It's easy, and you will see it soon enough. Yeah, so that's it. And so the key things to get out of this example are, first of all, how do you recognize whether resistors are in series or are in parallel? And the same is true of capacitors, but we're thinking about resistors right now. So if you must, and I emphasize the word must, if you must have the same current through each device, then those devices are in series with each other. Otherwise, they're not. If you, as far as parallel is concerned, if you have the same potential drop across multiple devices, then those devices are in parallel with each other. Next, so that's the first step, identify those. Second step, simplify your resistor network down to by finding equivalent resistances of subcomponents, parallel components, and then series components. And then calculate whatever you're after, and in this case we were asked to calculate a specific current through one of the resistors. That meant that we had to apply Kirchoffs loop rules, and so we did that. And the secret always is you have to write down the same number of equations as you have unknown currents. Even though I only wanted one of the currents, I needed to solve the system for all three of them. And a real real tricky part of these problems is labeling everything carefully and being careful with your label, with using your labels. So label them carefully and make sure as you're writing your equations that you use the labels that you've chosen carefully, correctly, and consistently. After that, you know, if 2 equations and 2 unknowns, you can probably do that by hand. 3 equations and 3 unknowns, forget it. Get your calculator or Sage or some other piece of software to do it for you. Okay, that's it for that. And so as far as the next recording, well, look on the list and see what I put there.